Wait, what about the gum?
What's that?
What about the gum?
What about the gum? Why don't you go spit it out? Do you mind if we use your smileys tonight? Is that okay?
No way.
No way.
I don't even mind.
You don't even mind? Okay.
No.
All right.
All
All right. How we doing tonight, guys? So I needed a second set of hands tonight, so Kylie gets to stay up a little later and help us out. And we're using a lot of Kylie's stuff, so I didn't think she'd mind. And if you're watching this live, feel free to ask questions as we're moving along. But otherwise, if you're watching this the next day, then hopefully everything we do here is relatively helpful. Say hi, Kylie.
Hello.
This is my daughter,
Kylie, and I'm 4 years old, and it's nice to meet you all.
Oh, I was going to ask you to introduce yourself. We already did that. Okay. Well, good. All right. So Kylie helped me tonight. We're going to do some simple probability. We're going to do some theoretical versus.
And we're going to do some subtraction and adding.
Who's running the show here? We talked about this. Anyway, so we're going to do some theoretical versus experimental probability. We're going to do compound probability, and we're going to try to keep this under half an hour. I don't know if it's going to work, but we're going to try, okay? So for starters, Kylie, I'm going to borrow some of your smileys here. Can you name me some colors that you have in here?
All colors of the rainbow.
All right, so give me 4 colors of the rainbow that you really want to use.
Red, pink, and purple, and blue, and...
Okay, that's 4. Perfect. So you said red, pink, purple, and blue?
Mm-hmm.
Okay. So we're just going to pick out a couple of red, blues, purples. Okay. So simple probability is exactly that. It's pretty simple. It's basically you're trying to figure out what are the chances, or what's the probability of getting a certain color. So you want to figure out what your chances are of getting something, I guess. So I guess some of the stuff is just better to just do it. So I'm going to put, we have 9. Let's make it an even number. We'll do another purple. All right. So on the table, I'll move this so you guys can see, but I have 2 blues. I have 3 purple. Okay. I have 3 red. I'm sorry. I take that back. I have 4 red and I have 1 pink. Okay. So, right. It is counting. Okay. Trust me, this stuff, you'll get there. Okay. So we have 1 pink smiley. Okay. We've got 4 red. Sorry, I should have capitalized that. How's Daddy's handwriting?
Good.
That's very nice. That's very nice of you. Okay. We got 2 blue and we have 3 purple. Okay. So in this case, our denominator is going to be 10. I'm going to add all these up. I'm going to add all the smileys I have here, which is 5 and 5. So I have 10. Okay. So all my probability is going to be out of 10. And this is what we call theoretical probability. This is if I were to run this test, if I were to pull out each one, then theoretically speaking, I should get the pink 1 out of 10 times. What are you doing? You're making me nervous. Okay, so I should be getting this 1 out of 10 times. I should be getting this 4 out of 10 times for the red. I should be getting 2 out of 10 for the blue, and I should be getting 3 out of 10 for the purple. So we always talk about we need to reduce our fractions. So I can't reduce 1 out of 10 anymore, but 4 out of 10 I can reduce down to 2 out of 5. What are you doing? What are you doing? You helping me or not?
Hell yeah.
Okay. So let's see. So 2 out of 10, I should be at a 1 out of 5. 3 out of 10, I can't really reduce. Okay. So these are what we call our theoretical probabilities. If I were to put all these in the cup, and I were to pull them out and replace them, then theoretically speaking, 1 out of 10 times I should get a pink. 4 out of 10 times I should get a red. 2 out of 10 times I should get a blue. And 3 out of 10 times I should get a purple. The purpose of it, though, the purpose of understanding probability is knowing which one you have the best chance of getting. So we're going to ask Kylie. We're going to see if Kylie knows. So Kylie, which color do you think you should choose if you want to win? So what you're going to do is you're going to pull a smiley out of here, and you're going to try to guess that you got the right one. Okay?
Which one?
Well, which one do you think would be the best one to pull out? There's one pink one. There's 4 red ones. There's 2 blue ones and 3 purples.
I think I'm gonna pick pink.
You're gonna pick pink? Why are you gonna pick pink?
Because I like that color.
Okay, but do you think that's the best one to pull? Which one has the most?
4.
4. What color is that?
Red.
Red. So if you want to beat Daddy and you want to guess the right one, which one do you think would be the best one to choose?
Red.
Why?
Because it has the most of one.
There you go. All right. You all with me on this one? Okay. So let's see if Kylie can pull a red out. Okay. Don't look. I said don't look. What are you doing, cheater? What'd you get?
Red!
What'd I tell you? Okay.
I got it.
You did. Okay. And that's because there were 4 reds in there. All right. So you're most likely to get a red. Okay. But at the same time, 4 of them are red, but 6 of them are not. Okay. So this is what we call complementary probability. Okay. So I'm going to write this on here. So complementary. All right. So complementary probability means that, so Kylie chose the red ones because there's 4 out of 10. She knew there was the most of the red in there. So that was her best odds of beating me here. Okay. But there's also, so there's 4 out of 10 that are red, but there's also 6 out of 10 that are not red. Okay. So there was actually a 6 in 10 chance that she wasn't actually going to pull a red one. But if she was going to guess any color, red would have been her best choice because there's more red in there than any other color. Okay. So this is simple probability. We're just looking at, things out, in this case, out of 10. Okay. We have 10 items in here. Pulling one randomly. What are the odds of pulling each one, or what is the probability of pulling each one? Okay. And we put that in a fraction because probability is supposed to be between 0 and 1. Okay. And so fractions or decimals will both show you probability between 0 and 1. And I'm going to focus primarily on fractions tonight, but I'll do a little bit of decimals as well if I have time. Let me see. The chat's kind of cut off tonight. I'm not sure what's going on. Let me see if I can zoom that out. Here, hold this, will you?
Sure.
Thank you. My assistant, Kylie. There we go. Okay. I had it zoomed out a little too much. Okay. You should give her private lessons on multiplication and division. Please don't. I will not. Yes, they all equal 1. That's right. Yep. If I were to add all these fractions up, they would equal 1. So again, that's how you know that you that your probability is fair, is because all of your fractions should add up to equal 1. Same with your complementary probability. The odds of something happening, or the probability of something happening in this case, is 4 out of 10. So the probability of it not happening needs to complement it. It needs to add up to equal 10 out of 10. So in this case, marker please. Okay, complementary probability means 4 plus 6 should equal 10, okay, because complementary probability should add up to equal 1, okay? So that was our first experiment, whereas we talked about, just drawing things out randomly. So next thing we're going to do is we're going to talk about theoretical probability, and we played skunk in my room, and I don't know if the other math classes did. And sorry, I'm kind of like on a weird angle there. So we talked about theoretical probability versus experimental probability. Okay, so we're gonna do this one a little easier. We're gonna start with just one dice here, or with one die. Okay, and theoretical probability means what I should get in theory. So before I run an experiment, what should happen? Okay, so Kylie, can you do me a favor? Can you tell me how many numbers are on there? How many different numbers are on the dice?
6.
There's 6, right? What are the different numbers that I can get?
10.
No, on the dice, you goof. What numbers can I roll, babe? Can I get a 1?
Yep.
Can I get a 2?
Yep. 3, 4, 5. 5.
What about a 6? Can I get a 6?
No.
I can't get a 6?
Yeah.
Is there a 6 on there?
Yeah.
Where?
Right here.
Oh, well, there you go. So 6. So these, Kylie, and anyone watching, these are all the possible outcomes that we could get with a fair 6-sided dice. Okay, so these are the possible outcomes. Okay, and so on the test, when you're asked what are your outcomes, well, these are them. You have a 6-sided dice. Okay, 6-sided number cube. So that means that you have 6 numbers on here. Okay, 1 through 6. So those are my possible outcomes. Okay, now theoretically speaking, I have a 1 in 6 chance of getting any of these numbers. Okay, so when we're talking about my probability of getting a 1, a 2, a 3, a 4, a 5, or a 6, So I'm going to make my table here. Okay, I have a 1 in 6 chance of getting a 1. I have a 1 in 6 chance of getting a 2. A 1 in 6 chance of getting a 3. A 1 in 6 chance of getting a 4. And a 5 and a 6. Okay, so the reason that we call this a fair dice is because we have the same chance of getting every number. Okay, and it's not weighted or anything like that. What if it's not fair? Well, that's a good question. That's called cheating, and that's not something that we'll talk about with this kind of probability. Okay, what do you think?
I think that's great.
That's the spirit. All right. Where are you at? Why don't you scooch down the bench so we can see you? You're all the way. Yeah, there you go. See, now we can see you. Okay. So you can hang right there. All right. So that means, in theory, if I were to roll this dice 6 times, then every number should show up. Okay. But in reality, that's not what's going to happen. Okay. That's not usually what happens. So again, this is called theoretical probability. And this type of probability, because every answer is the same and it's 1/6, we call this, I'm going to use a different marker. Hopefully it shows up. Okay, we call this a uniform, I can't write today. This is called a uniform probability because it's all the same. So I like to, I look at it like this. If I go into, Kylie, what's your favorite restaurant? What's your favorite place to eat?
The place, Olive Garden, where you get the big meatball.
Oh, you like Olive Garden, right?
Because they give you a big meatball.
You like the big meatball?
Yeah.
You're funny.
That's my favorite.
I told everyone how much you like Thanos today, by the way.
Yeah.
Yeah.
I can tell.
Yeah, they all think you're crazy.
And Captain America and Captain Marvel, too.
Yeah, I did. I told him. So, but I told him that you like to play with the gauntlet. You like to pretend like you're using the Infinity Stones. But anyway, back to the story. So you like Olive Garden, right? Mm-hmm. Now, is everyone at Olive Garden that works there, do they dress the same? Do the servers all dress the same, all the people that bring us our food?
Yeah.
Yes. Okay. What do they wear? Do you know?
They wear aprons in case they have to cook.
Yeah, and in case they spill food on them, right? So they have a uniform on, right? They all look the same. So that's why a uniform probability, all of the outcomes have the same probability, so they all are uniform, is what we say. So in this case, if I roll this dice 1 time, okay, so I have a 1 in 6 chance of getting any number. All right, I got a 3 on that one, right, Kylie? Okay. So the difference between theoretical and experimental probability is theoretical is what we mathematically figure out should happen before an experiment is done. So I like to say before, we like to figure it out in theory, okay? But when we run experimental probability, then, it isn't always going to work out perfectly. So we're going to roll this dice 6 times and we're going to see what we get, okay? So we're going to go from theoretical to experimental probability. Here's our outcomes, all right? And we're going to tally up how many times each number shows up, okay? I'm going to erase this. Kylie, would you roll the dice for me, please?
Of course.
Thank you, dear. Okay, go ahead and roll it. Okay, what do we get?
A 5.
All right, so let's put a tally on the 5. Ready? Okay, roll it again, please. What do we get?
1.
All right, keep going. We're rolling.
6.
Good. Okay, keep rolling. Oh, what's that?
3.
3. Hey, so far we got all different numbers. Okay, roll again. Go.
3.
Another 3. Okay. And a 6. Okay. So I see someone asked, Black Camera Photography asked, what is the definition of theoretical? So theoretical probability is what we think should happen before we actually start rolling the dice. So theoretical probability, we had said, was I have a 1 in 6 chance of getting every number, okay? But experimental probability is when we actually roll the dice. So we rolled the dice 6 times. And even though we had a fair chance of getting every single number, not every single number showed up, okay? So in this case, our experimental probability was different, okay? So for 1, okay, we had a 1 out of 6, okay, which is what we anticipated for a theoretical probability, right? It was uniform. They were all 1 out of 6, okay? But for 2, we had 0, okay? So we didn't even have a 2 show up, and we rolled 6 times. For 3, okay, we had a 2 out of 6, so we had one out of 3 of our rolls was a 3, okay? So now 4, again, we had 0, didn't show up. We had 5, okay, and this we had, again, 1 out of 6, and that matched our theoretical probability. And then we have 6 here, which again was a 2 out of 6, which equals 1/3. So even though this is a fair dice, okay, we anticipated that 1 out of 6 times we should get every number. We only rolled this dice 6 times. So that was the experiment that we ran. So that's the way I like to explain experimental probability, is when you actually run an experiment, you roll the dice a couple times and you see how many times each number shows up. Okay, so in this case, we did that. We rolled the dice 6 times. Theoretically, we should have got every single number, but experimentally, running this experiment, we didn't get every single number, and in fact, we got 2 numbers twice. We got 3 and 6 more than the other numbers. Okay, so one thing that we need to realize too is the more times that we roll the dice. One second, babe. The more times we roll the dice, the closer we actually get our experimental probability to equal our theoretical probability. It almost never will be perfect. But if I were to roll this dice 1,000 times, hey Kylie, should we roll this dice 1,000 times?
No way.
Why not?
Too many.
Why?
Because that's way too many.
Is that way too many? Is that gonna take too long?
Uh-huh.
Okay. You sure?
Uh-huh.
All right. Get your finger out of here. You're on camera. People are looking at you. Have to take a little pride. So anyway, so if we were to roll this dice 1,000 times, which we're not gonna do because we don't have that kind of time. These numbers, these fractions would actually end up getting closer to our theoretical probability, which was that 1/6, okay? Because again, we had a uniform probability. Every number has about a 1 in 6 chance of showing up. And so the more times we roll the dice, the closer each of these fractions will end up getting. And so to kind of prove that, Kylie is going to roll the dice, how about 6 more times?
Okay.
Is that okay? So hold on, I'm going to adjust our fractions here. So our fractions are going to be, we're going to make them out of 12, okay? So we're going to do, everything's going to be out of 12 because we rolled the dice 12 times in this experiment, all right? And we're going to see if we can get the distribution here to be a little bit more even. So go ahead, Kylie, roll.
1, 2, 3, 4, 5, 6.
What do we get?
1.
Roll again. Keep going, keep going. Don't take forever.
5.
All right.
Let's see if we get 4.
You bring here 4.
6.
Another 6.
3, 6.
Keep going.
2.
Hey, we got 2.
We got our first 2.
There we go. 2 more rolls.
5 again.
Oh, man.
2 again.
All right. Did we get a 4?
No.
We didn't get a 4.
I need 4.
Okay, but we got 2 to show up twice. All right. So 1 was still 2 out of 12 now. So that was 1 out of 6. So that stayed about the same. Now 2, we got twice out of 12. So again, 1/6. Okay, 3 showed up twice now. So we have another 1/6. But 4 still didn't show up. Okay, so we still have a 0 for our experimental probability. And then these numbers here, okay, 5 and 6, they both got 3 out of 12. Okay, so that means that every one out of 4 rolls was one of these numbers. Okay, so again, not perfect. Okay, we're not perfectly at 1/6, and it's going to spread out a little bit more as we keep going. But again, the more times you roll this dice, the closer we're going to get to getting each number about the same time. Okay, so that's the difference between theoretical and experimental probability. Is theoretical probability is before you roll the dice or before you do an experiment, you decide what are your chances of this happening. And then experimental probability is when you actually run the experiment and see how many times that number shows up on the dice, how many times you flip heads or tails, okay, or how many times you pull out a smiley from a cup, okay. So let's see, this ain't ELA or social studies. Can we go over the Treemaps? Treemaps, oh, I love Treemaps. Kylie, do you like Treemaps?
Yeah, but how come you get to do all the talking?
Because I'm the one that's got to do the teaching. What do you want to say that you haven't said? Well, you say hello. I'm going to clean the board. Go ahead. What do you tell them everything you want to know? Go ahead.
I don't think I want to say anything.
Why?
I just want to listen.
You want to learn about probability?
I just really want to talk with you too.
I know, babe. Well, you can talk to me. Go ahead. I've hurt her feelings now. Did I hurt your feelings?
No.
Oh, well, you sound like I hurt your feelings. Where's the other dice? Did we have another one?
I had it.
You goofball. All right.
Where's this one?
So, if students talking about Treemaps, okay. So let's talk about, now we're rolling 2 dice. So actually we're going to start getting into what we call compound probability. Okay, compound probability is when we have one event happening and then another happening. Okay. So Kylie, what are the choices for numbers on the dice? What are the numbers that we can roll?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6, right?
Yep.
Okay.
That's the only numbers on the dice.
Okay. So you roll this dice. Okay, go ahead. So Kylie rolls the first dice. Okay, go ahead. What'd you get?
2.
All right, so Kylie got a 2 on the first roll. All right, so these tree maps, what they do is they decide what can happen first and then what can happen second after this, okay? There we go. And excuse my crazy trees because, of course, I chose dice, which has a ton of results here. So, Kylie, you're going to roll this dice. Can you roll this dice for me?
Here's a smiley.
What are you doing with that? Okay. What are the numbers on this dice? Can you tell me?
1,
Yeah. 1,
2, 3, 4, 5, 6.
3, 4, 5, and 6. Okay. So that means the first roll could be any of these numbers, and the second roll can also be any of these numbers. So now we have a 1 in 6 chance of getting any roll. Okay, and we're actually we're timesing this by another 1 in 6 chance. So that means any combination of these two numbers, we now have a 1 in 36 chance of getting any of these possible combinations. Okay, so the tree maps, okay, or the tree, when they show you the sample space, these are the possible outcomes. Okay, and so we're just kind of drawing them all out so that we can see them. And I look at it like you're following a roadmap. Okay, so if you start at a 2 like Kylie did, okay, Kylie, roll the second dice, please. So she started at a 2, and we can wind up with any of these results. Go ahead, Kylie.
I can do this one.
Well, let's leave the 2. That was the first dice. I like that one. That was a good one. Plus, I got some red marker on there, so my bad.
It's okay.
Okay, roll that dice. What'd you get?
6.
All right, so Kylie started with a 2, and she ended with a 6. And that was one of our possible outcomes out of 36. So that's a 1 in 36 chance of that happening. This is talking specifically about getting each number in this order, okay? So basically, I'm just listing all the possible outcomes that I can have. 1, 2, 3, 4, 5, 6. Now, this isn't talking about which numbers I get most. This is talking about getting these specific rolls, okay? Kylie, do you have your coin?
What coin?
Remember that coin you had? Where'd that go? Didn't you have a coin? Am I making that up?
When you two were doing that magic trick, I don't know where it went.
Oh, okay. Well, can I use one of your smileys as a coin?
Sure.
Okay.
Or you can use one of my coins from my piggy bank.
Well, let's use this one, okay? Because we're right here. All right. So let's say Kylie was going to flip a yellow smiley, green smiley, and give me another color. How about blue? And a blue one. Okay. So she's going to flip 3 coins. Okay. So she's going to flip coin 1, which can be heads or tails. Okay. So Kylie, flip that coin. So we can get heads or tails, right? Go ahead, Kylie. She flips the coin. Flip it. You know how to flip it? Throw it up in the air. All right. We got what? We got heads. Okay. All right. So now Kylie's going to flip the green coin. Okay. And her choices here are the same. They're heads or tails. And if she had gotten tails, her next choice here would have been the same as well. Okay. Go ahead and flip it. And what'd you get?
Head.
All right. So we got heads again. Okay. And now if we flip the third coin, okay, we can get the same choices. We can get heads or tails. Okay. Heads or tails. Heads or tails. Heads or tails. All right, go ahead. What'd you get?
Tails.
Tails. So she got heads, then she got heads again, and then she got tails. Okay, so that's how these tree maps work, is they lay out all of the possible outcomes. Okay, and we can actually multiply how many outcomes there would be. Okay, because we have a 1 in 2 chance of getting heads or tails. We're timesing that by another 1 in 2 chance, right? There's 2 of those. Okay, and we're timesing that by another 1 in 2 chance. All right. So this means that we have a 1 in 8, because 2 times 2 is 4 times 2 is 8. So we have a 1 in 8 chance of getting any of these possible outcomes. So what this means is there's 8 possible outcomes here for flipping this coin 3 times, because whether I get heads or tails, okay, the next event is going to be the same, but it kind of branches off that first one. So if I get heads, I have an opportunity to get heads or tails again. If I get heads, I obviously have a chance to get heads or tails again. In this case, Kylie got tails. Okay. When did we do that? We did the tree maps earlier on in my class. And I talk about that when we talk about sample space. Okay. So these, again, they label all the possible outcomes. All right. But sometimes they can tell you something different. Okay. So Kylie, can you get me something to, I heard somebody. Can you give me one of Mason's wipes, please? So I can wipe off the board. Thanks, babe. Boy, it's really nice to have help around here. It's hard to find. And then we're going to do, how much time we got? And then we're going to do one more experiment. We're going to talk about, this is compound probability. This is where you have multiple events happening. And when you have compound probability, you multiply those together in order to show how many different results there would be. So, any luck? And then the last thing we're going to talk about is when you do compound probability without replacing. So, like, let's say you draw a card, but then you leave that card out. We're going to talk about that next.
Here you go, Daddy.
Chromebooks shut down at 10 p.m. Yes, they do. That's a new thing they're doing. So, but don't worry. I'm going to be done in the next 5 minutes or so. I don't need a whole lot of time with this. So I just wanted to clean my board here. Thank you, Kylie. Very helpful.
Okay.
Yeah, are you about ready for bed?
No.
No? You're going to get me in trouble. You're not supposed to be up this late. Okay? It's all right. We break the rules sometimes, don't we?
Mm-hmm.
For the sake of it, you're here to help the math class out. So, you know.
Well, you did say if I helped, I could stay up later.
Don't sell me up the river here. Don't get me in trouble. All right. So, all right, give me the dishcloth really quick. Hurry up. This is all wet still. All right. So the last thing we're going to talk about here, well, not the last thing. One of the other things I want to talk about with dice is something to think about. Yeah, it's still wet, babe. Not the dish rag. Get me the one that's hanging on the oven.
Oh, I can do that.
Oh my gosh, good help is so hard to find around here. It's ridiculous. Thank you. All right. Now we're in business. And if mommy asks how that got dirty, we'll say Mason did it, okay?
How come?
I'm just kidding. It was a joke. It was a joke. We'll be honest. I'll tell the truth. Maybe. Okay. So.
Very funny. Okay, Dad. Very funny.
You were made for the camera. All right. So when we're talking about the dice here, we're talking about how there's 36 different outcomes here. All right. But at the same time, some people have been making the mistake in thinking on the dice, what are your possible outcomes? Okay. And this is one of the problems that we had in class today is what are the possible numbers that you can get when you roll 2 dice? So what's the smallest number you can get?
1.
Is it 1, Kylie? Because I rolled 2 dice. Can I get a 1 when I roll 2 dice?
No.
So what's the smallest number I can get then?
2.
It's 2. Okay. So I can only get a 2. I can't get a 1. All right. Just because I have the, I don't know how to explain that any further, but again, I can't roll less than 2 on a dice because, I can't just roll 1 die and I don't have a 0 on this die. So my smallest result is actually going to be 2. All right. And then Kylie, what are all the other numbers I can get when I roll 2 dice? Well,
we can get 3, 4, or 5, or 6.
Any others?
7, 8, 9, 10. 11, 12, 13,
Okay.
14.
Can I get 13 on a dice?
No,
because I get 12 is the biggest number I can get. All right. So here's the mistake people make is they think that I have a 1 in 12 shot or 1 in 11 shot of getting all these numbers equally on the dice. But if we look at our tree map here, or if we look at our sample space of all the different outcomes, there's only one way out of 36, okay, because I still have 36 possibilities, but there's only one way that I can get 2, and that's if I roll a 1 and a 1. All right, so getting a 2 when I'm using 2 dice, okay, there's actually only 1 in 36 chances of getting that, okay? And I was talking to my classes about this today, so, these are things that we have to think about. So this is the time of year, it's May 20th, okay? People need to slow down. The year is not over yet, okay? So you got to slow down, got to read things carefully, okay? and this is where that really comes into play. All right. So now, how many times can I get a 3? So if I add 1 plus 2, okay, and that's what I can get 1 plus 2 here, and then 2 plus 1. But there's no other way. I can't get a 3, a 4, a 5, or a 6. Otherwise, I can't get a 3. Okay, that would be too much. So I have to either roll a 1 or a 2. If I roll a 1, I have to roll a 2. If I roll a 2, I have to roll a 1. Those are the only ways I can get 3. So there's actually only 2 possibilities out of 36. Okay, same with the 4. Okay, I can roll a 1, a 2, or a 3. But then I have to roll, if I roll a 3, I have to roll a 1. If I roll a 2, I have to roll a 2. If I roll a 1, I have to roll a 3. So I only have 3 ways that I can get 4 on the dice. Okay, and we're seeing what's happening here. Each time, there's more, the bigger the number for now, there's more opportunity. Okay, so same with the 5. I can roll a 1, a 2, a 3, or a 4. But then I have to get, with the 4, I have to get a 1, a 3, I have to get a 2, 2, I have to get a 3, 1, I have to get a 4. So again, I have 4 possibilities out of 36. Okay, and you can see there's a pattern here. I can get there's 1 possibility here, there's 2 here, there's 3 here, there's 4 here, and guess what? There's 5 opportunities to get a 6. Okay, so I have a 5 out of 36 chance. And again, I'm not reducing these right now, but if you've ever heard the term lucky number 7, okay, that's because on the dice I can roll a 1, a 2, a 3, a 4, a 5, or a 6 because they're all less than 7, and if I roll any of these numbers, then there's at least one number that will pair with it to make a 7. So getting 7 when you're rolling 2 dice is actually the best probability because there's actually 6 out of 36, or exactly a 1 in 6 chance of rolling a 7. So if you're ever rolling 2 dice, you're more than likely going to get a 7 than any other number. Okay, right, Kylie?
Yeah.
Am I boring you?
No way.
All right, that's the spirit. Okay, because then when we start getting the bigger numbers here with an 8. Okay, now I have the opposite problem. I can't roll numbers that are smaller. Okay, because if I roll a 2 or if I roll a 1, there's no 7. Okay, so I can never, if I have a 1 up, I'll never get an 8. Okay, so I have to roll at least a 2, and then if I roll a 2, I have to get a 6. If I roll a 3, I have to get a 5. If I roll a 4, I have to get a 4. If I roll a 5, I have to get a 3. If I roll a 6, I have to get a 2. So now it actually starts to go back down. Okay, so each of these numbers actually is kind of like a mirror of the top numbers. So 4, 3, 2. Okay, and if you think about it, there's only one opportunity on the dice to get 12, right? 12 is just as rare as getting snake eyes because there's only one way to get 12 here. So there's actually only a 1 in 36 chance. All right. So this is what I wanted to show you, is because sometimes we make the mistake. Our brain makes us think that we are looking at uniform probability, where we think all the odds are the same. So if we're looking at every single possible dice combination, then yeah, every single one of them has a 1 in 36 chance. But if we're looking at every number when you add them together, then that compound probability looks a little different. Okay, and we have to look at how many opportunities we have to get a 2, a 3, a 4, a 5, a 6, a 7, which is the best in this case because it's the highest probability, and then it kind of goes back down. Okay, so again, this comes down to slowing down, reading, and looking carefully at what you're doing. I tell you that all the time, don't I?
What?
I tell you to be careful about what you're doing, right?
Not because you might drop something you're trying to eat.
Yeah, so if you're walking with a big glass full of milk,
Or a big glass full of spaghetti.
With a glass full of spaghetti?
Oh, yeah. I mean a big bowl of spaghetti.
Okay.
A small bowl of spaghetti. And a lot of it was in it.
Yeah.
Would it spill?
I don't know. If you're holding it, I would bet on it. I don't know why you're walking around with a bowl of spaghetti, but what do I know? All right. So the last thing I'm going to talk about is, and Kylie's going to help me out, and I know she's been very eager. Okay, we're going to talk about compound probability when you are not replacing something. Okay, so, what do we do with the drug? Okay, sorry.
You mean the blue one?
No, the one that's on Mason's tray over there. Is he sleeping up there? I haven't heard him. Have you?
I think he's sleeping.
All right, success.
He's been quiet.
I know, right? We're pretty lucky today.
We're not even waking him up if we're being loud up here.
Are we being a little loud?
I think so.
Yeah, just a little bit. We're having a good time though, aren't we?
I'm having fun doing this video with you.
Well, good. I know that the kids will be happy to see you. Okay.
Yeah.
Oh, man. You know what's weird is one day you're actually going to go to the school that I teach at.
Mm-hmm.
Are you excited about that?
But I don't think that And you're gonna teach me, right?
No, you'd be in another class.
Because everyone knows me.
Well, I mean, you and I know each other, so.
Mm-hmm.
All right, that's another topic. But anyway, the last thing we're going to do is we're not playing Crazy Eights. I know Kylie loves Crazy Eights. Oh my gosh.
I sure do.
She loves Crazy Eights. Okay, why is this 3 in here? Get this out of here. Okay, so what I have here is I have one of each blue card. Okay, so I have a ace. So we'll call this 1. I have a 1, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and a 10. All right.
Mm-hmm.
So when you are pulling cards here, okay, well, so I'm gonna have Kylie pull a card in a second. All right, and let's say we're talking about the odds of pulling, or we're talking about the probability of pulling an odd number 2 times.
Because odd numbers are the ones where you got the ones, right?
They're the ones that are. Hold on one second. Thank you.
Oh, we got you right first.
Thank you, babe. You know I can't do 2 things at once, right?
Okay. I mean, sometimes.
Sometimes. So we're gonna see what's the probability of pulling an odd number twice if I put the card back. Okay, so Kylie, go ahead, pull a card. What did you get?
I got.
Show them, not me. What'd you get?
10.
All right, is that odd or even?
Even.
Okay, so we didn't get our odd one. Okay, let's go again. Let's put it back and go again.
Mix it up, okay?
Yes, ma'am. All right. Go ahead. You got the same card again. That's just crazy. All right. So in this case, okay, we look at the odds of getting an odd number twice. Okay. So if we look at all of our possibilities, okay, we could get an odd number twice. We could get an even number twice. We could get an odd and then an even, or we could get an even and then an odd. Okay. So if there's 4 possible choices, the odds of getting 2 odd number cards, the probability of getting 2 odd number cards if you replace is a 1 in 4 chance, right? Because I have an odd twice, that's right here, and that's 1 out of 4 possibilities. So I have a uniform probability of 1/4. Okay, so I could get an odd number twice. I can get odd then even then odd, and then even. These are my 4 possibilities. Okay, so if we look at the math on this, okay, I have a 1 in 2 chance of pulling either an odd or even card. Okay, and if I times this by that same opportunity again, all right, so I have a 1 in 2 chance again of getting another odd card. Okay, this ends up equaling a 1 in 4 chance. So that's where those numbers come from. Okay, so this is if I'm going to replace the card. And this is what you really have to pay attention to on your test, is there might be an opportunity where you don't replace the card. You have to read carefully because it might say in big bold letters, not replace. Okay, so if you choose not to replace it. So we're going to do this. We're going to talk about this again. Okay, but we're going to talk about the odds of pulling a odd number twice, but we're going to say without replacing. Okay, so without replacing. Oh no, where's that dish rag? Mommy's gonna kill. We're gonna be in big trouble with mommy, aren't we?
Yeah.
Look at what I did. Are we in trouble?
Yeah.
I'm gonna blame it on you. Is that okay?
No.
Why?
Because I don't want to be in trouble.
I know it's my fault, and there's video evidence that it's my fault.
You could have just used a wipe and just made it dry with your hand.
Well, that's what I was doing before, but now look at my hand; it's all red.
I know.
Telling me what to do the rest of my life. All right. So anyway, so now I'm going to pull 2 cards, and I'm not going to replace them. And when I say I'm not going to, I mean Kylie's not going to. Okay. But let's talk about let's talk about what this means mathematically. So right now I have a 1 in 2 chance. Okay. I have a 50-50 shot, or I have a 5 out of 10 chance because I have 5 odd cards out of 10 in this pile. Okay. So the odds are pretty much, or the probability is pretty much the same that Kylie could pull either an odd or an even number card. Let's see how she does. Go ahead. Are you looking? You're peeking, aren't you? Look at her. So what is that one?
A.
So ace is our 1, right? So Kylie did it. She pulled out an odd number card. So we are not going to replace this. We're going to set this aside. Okay. But now we have to think about, Kylie, I have a question for you. We had 10 cards. You took 1 out. How many cards are now left?
9.
There's 9 cards left. So that means that our next pull is going to be out of 9. All right. And Kylie, if you pulled out 1 odd number card, okay, how many of them are still in here?
9.
Well, there's 9 cards in here, but how many of these numbers are odd? There's 1. There's 2. How many of these are odd?
5.
Well, there's 5 odd ones. You pulled 1 out, so how many are left?
4.
There's 4. Okay, so as Kylie just told us, a little bit of help. Okay, we pulled out an odd number card, so now we have 4 more odd number cards left, but there's only 9 cards left, so now our denominator is different than the first time. So this is what happens when you don't replace, is now you have a different denominator because you only have 9 cards to choose from, okay? So this changes the odds a bit. All right, and let's see if Kylie can do this. Can you pull an odd number card? Can she do it? Dun, 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 dun. What's that?
Even.
What is it? You got a 10 again.
For the 3rd time.
All right, so Kylie couldn't do it this time, and that's okay. But if we multiply these together, we'll take a look and see what the probability of this happening was. Okay, so we end up getting 1 times 4 is 4 over 18. Okay, and both the top and the bottom can be divided by 2 to reduce. Okay, so we end up getting 4 divided by 2 is 2. 18 divided by 2 is 9. So we actually have a 2 out of 9 chance for this probability to happen. Okay, so again, we only change the denominator when we are not replacing. So in this case, we didn't put the odd number card back. Okay, so we pulled out an odd number card, we didn't replace it, and then we tried again. But again, that changed the probability because we had 9 cards and only 4 of them were even at that point. So this is actually less than 1/2 of a chance. So after you've pulled an odd number card out, it actually becomes more difficult to pull another one out. So these are things we have to think about when we're doing our test. All right, you're being weird. So that is all we have for today. I didn't see a whole lot of questions, and I think the questions that were asked got answered. So tomorrow, feel free to use this as you're studying, as you're doing your study guide, and hopefully this gives you just a nice little rundown of all the different things that we talked about in class. So if you have any questions, you know where to find me. While you're doing your review, you can always message me on GoGuardian. I'd be happy to help you out any way I can. And I will do my best to timestamp this video, but it looks like it's only going to be about 45 minutes, so it shouldn't be too hard to navigate. And Kylie, thank you for helping us out today.
You're welcome.
Is there anything else you want to say to the kids?
Thank you for seeing us, and we'll see you again soon.
Okay, thank you again, and have a good night. Say bye.
Bye.
There we go.